Good day. Welcome to When Autoscaling is Not Enough. My name is Ignacio Nin. I work as an SRE at Remind. My job includes keeping the system running smoothly, writing the automation for both our infrastructure and our application deployment, and planning for future user and traffic growth. I've been through some bumpy times during my tenure at Remind, possibly the most notorious one being the recent onset of COVID-19, which hit Remind in a really particular way. And today I want to share with you some bits of that, how we navigated through it, and some of the lessons we learned about how we do and how we want to do stuff. First, let's talk a bit about what Remind does. Remind is a communication platform that allows educators to reach students and parents where they are. It's built for education and comes in the form of text messaging, smartphone, and web notifications. Our vision is to give every student the opportunity to succeed. Remind is currently present on 80% of public schools across the US, and it's reaching 60% of its teachers. Currently, this means that Remind is delivering about 10 million messages per year for 30 million monthly active users. And since we've got a crucial role in the students' education, we've got a strong commitment to ensure a timely delivery for every single one of those messages. In order to get some context about the issues we faced on the COVID's onset, let's do a quick review of Remind's infrastructure basics. So we lean heavily on hosted services for our business. Most of our infrastructure lives on the AWS cloud, but uses some other external services too, like GitHub for code hosting, Datadog for monitoring and logging, and some other examples. The advantage of hosted services is that we leverage external systems to do our heavy lifting. However, the other side of that coin is that we inherit the limitations from the services we use. This will be an important factor in one of the points we're going to discuss in the talk. In order to manage this in a scalable and reliable way, we keep a strong commitment to fully describe a system that's infrastructure and application stack in code. For this, we leverage AWS CloudFormation, which manages all of our AWS resources, plus some external resources too. CloudFormation uses a declarative language for its templates. So once the operation reaches a certain size, you will need some tooling to manage those templates. For that, we use Staka, originally developed at Remind and based on Troposphere, which allows us to write templates for CloudFormation using Python. So this adds an imperative layer on top of CloudFormation in which we leverage all the power of this programming language, which we pair up with another declarative layer, which is the configuration that commands those Python programs. So this last layer is our DSL for the infrastructure, which allows us to execute infra-wide changes with little changes in configuration, usually a change on a text file. For example, global variables that affect every cloud resource, tags, etc. Having also control over the Python layer allows us huge flexibility on managing resources, existing and new. This is our approach to infrastructure as code. In regards to our application, Remind has a microservices architecture, having about 60 active services, all of them engaged in continuous deployment with several releases every day. The microservices themselves are written in a diverse set of languages and platforms. From the infra side, we place no restriction to the platform the developer needs or wants to use. The way we can achieve this empowering the developer, is by leveraging Docker. We specify a common interface the application must conform to, and we encapsulate that into a Docker container. Hence, all applications work as a black box when looked from the infrastructure side, and this allows them to play together well among themselves. This common interface also plays well with the infrastructure as code paradigm. When a new application is ready to be released into a cloud, it's written into our infrastructure repo with a pointer to the new app's code repo. And so its CDI, CD pipeline, its monitors, its dashboards, load balancers, everything it needs are created in an automated way, and the application is ready to run as soon as it's encrypted on our infrastructure repo. The applications conform also to the 12-factor paradigm. So every resource the application needs, storage, compute cloud, maybe a database, are placed globally in the infrastructure and are not as part of the app. This is essential to our approach to scaling, as we will see shortly. After this brief introduction into how our infrastructure looks like, let's take a look into Remind's quite unique traffic pattern. So our pattern is perhaps a more extreme version of the classic snake and elephant double bump. Being an education platform, the traffic maps clearly to the activity in the schools across the US. The activity in the morning and the peak is an order of magnitude higher than during the night when our traffic is almost flat. An interesting thing to note here is that we have our peak traffic coming just a few hours after we started handling any traffic, because we're starting from the lowest point and going to peak in a few hours. This has consequences in how quick we need to react, and we will see how that comes into play in a few moments. This variation in traffic happens not just daily, but weekly, with lower activity during the weekends, and yearly too. After an expected low activity during the summer, students go back to school in August and September, traffic ramps up, and these two are among the busiest months we have in a year. Traffic usually reaches a new high every September, and then largely stabilizes during the year. After several of these cycles during the years, we have grown used to hone up our systems during the summer, and we usually can cruise what we call back to school, which for us means a new traffic, safely. Now, this traffic pattern, this shape, poses a challenge for managing the cost of our operation. If we scaled permanently according to the peak traffic, we'll be wasting cycles, not just during the night, but also 2 days a week and during the whole summer. So in order to scale our systems according to the time of the day, the time of the week, and the time of the year we're going through, we need dynamic scaling. So the solution we're using for this is to leverage autoscaling. Autoscaling works by tracking a live metric from a system, usually CPU. And as CPU goes up and down in a certain direction, autoscaling will scale in or out the resources for us, spanning or removing new resources, containers, load balancers, everything we need so that the metric is kept under control. 2 places in which we use autoscaling are compute cloud and our database cloud. For the compute cloud, we need autoscaling at 2 levels. First, the Docker level. Every application in our microservice architecture has itself a unique pattern, a unique traffic pattern too, and we must be autoscaled independently. So we track, also usually, average CPU for each one of them, each one of the applications, and we set lower and upper limits for the application, how many containers to launch, as part of its description in our infrastructure DSL. So autoscaling here scales in or out containers as needed as part of the application configuration. Now, at the cloud instance level, we need to make sure that we have enough computing power for running those Docker containers. So the instances are autoscaled too, according to some other set of parameters globally. Some challenge that the compute cloud has for autoscaling is that tracking CPU alone might be insufficient. The applications can not just be CPU bounded, but depending on the workload, we have I/O bounded applications, memory bounded applications, etc. So a solution for this could be to track a lower CPU setting, to control a lower CPU set, but that could be a burden to cost in a new CPU. So one thing we're trying right now to tackle this is to enforce minimum quotas by instance type. So apart from CPU heavy instances, we keep a number of memory heavy instances too, or some other types as we need. So this ensures that any new app that wants to launch, any new container that needs to be launched, at any time has enough spare, not just CPU, but memory, network bandwidth, etc. in the cluster to be launched and work properly from the start. As for the database cloud, we use Aurora RDS, Postgres, and this has some interesting consequences on how we architecture the solution. So our apps use 12-factor principles, and we keep the source of truth on these clusters. This meaning practically that we need our applications to write to a single target to ensure consistency among all of them. We may spawn as many readers as we need, read-only copies, to be able to send read-only traffic in a load balancer way to these copies. But our applications, all of them, need to write consistently to a single writer. So for autoscaling, we can autoscale readers, and we track reader metrics, in this case CPU2, and we spawn or remove copies as we need. However, the writer needs to be vertically scaled only and necessarily statically scaled. The limitations that this single writer architecture imposes have had an important role in our capability to react, as we will see shortly. So in general, we had become used to our own usage pattern. We had developed a certain response capability, which we thought made us able to withstand great waves of new traffic while keeping our costs under check. However, you can only plan so much, as we will see. So the onset of COVID-19 was a game changer for many things, among them, education. The importance of distance learning reached a new level, and this would mean for us a test like we hadn't seen before for our stability and resiliency. On the second week of March, we started receiving traffic we weren't yet able to explain back at the time. This was legit traffic, users existing, new users, but the bottom line, remind traffic ends up tripling in 6 weeks for certain metrics of it. So our reliability was put to test. There's only so much you can test in anticipation for these changes. You can test what you believe is going to be double traffic, but real, legit traffic is undistinguishable from a DDoS. It all started with an alert, probably by this one. So one of the most important aids in our ability to detect what was going on was not only having the data, but observing the data and having alerts telling us what was going on. This is an automated Datadog alert telling us that we have reached a maximum limit for autoscaling for a single application. It's essential to have maximums for every application because this prevents runaways. But deploy will use up all our CPU, and if you haven't got a stopgap, you will spawn and spawn and spawn, and you will reach nowhere. So we have maximums and minimums for every single application we have. So immediately we were ready to react. Paired with our infrastructure-as-code approach, we have a culture of no heroes. All of our team is empowered to jump in and adjust the infrastructure as needed. So in this case, this was legit traffic, so we needed to adjust the maximum to this new traffic. So what we needed was to change the maximum on that application configuration. So what does it look like in our infrastructure-as-code approach? A change, as you're seeing on a file, and a commit that leaves a trace of what was going on. Adjusting autoscaling for the compute cloud in principle was limited to adjusting to new levels, doubling first, then tripling, maybe more for some of the applications. This was paired up with sensible upgrades on our storage system, so larger as we needed, as any application needed larger storage, etc. We scaled it up. The database layer posed some unique problems that autoscaling alone wouldn't fix. So we needed to jump in and adjust that to be able to handle this new traffic we were having. As we mentioned at the start, the peak usage happens just a few hours after we started serving traffic. So our readers, our writers will go from 0 to 100 in really short time. And for the previous traffic, previous to COVID, we were launching readers with enough speed. However, we found out that the new traffic was pushing our readers close to 100% of CPU, and we weren't spawning new readers fast enough. Why is this? Well, launching a new div instance can take actually several minutes. It's not the same as launching a new container. Why is this? Well, you have 3 phases because you want to detect that the CPU has gone high, but you don't want to react to peaks, to a single peak going to 100, and you don't want to react there and then having to scale in back again. So you want to average, and you want to average across, say, 2 minutes, 3 minutes. So you are introducing a delay in detection alone. Once you have detected that you want to scale out, there's you need to copy the full data set into a new instance. And that, for large databases, say in the teras, can take a couple of minutes more. That it's idle time. The database is launching and you need just to wait for that. And even after it's launched, actually, this depends a lot on how is it stopped and the technology you're using. But oftentimes you cannot just send all the new traffic to the instance that has just spawned, because you have to warm up the cache. So traffic needs to slowly be started sending to the new instance, and you need to ramp up across some minutes more in order not to kill the new instance with the inrush. All this added up can take a few minutes, anywhere from 5 to 20, depending on the setup, depending on the cache, depending on several things. But for us, we found out that we wanted 10 minutes of reaction time. It's not that a new instance needed 10 minutes, but we wanted to have that time to be able to react. Now, the new traffic wasn't given us that time. So we decided to add scheduled scaling in addition to auto-scaling. So before we had these peaks on the o'clock times, which caused by scheduled message usually, and the responses, we forced instances to scale out 15 minutes before. So here you can see that 8:40 a.m., for example, we set the minimum reader cluster to a new minimum, and new instances were launched to keep that minimum satisfied. So when at 9 scheduled message went out, we were already ready to handle that. Then on the afternoon, we would scale back to 0, and we would allow the cluster to scale in as needed. So that allowed us to flatten the curve for the readers. And you can see here after that change that we were able to, we weren't peaking close to 100 again anymore. However, the single writer issue poses some unique problem too. Because during the peak traffic, we found that our writer box, which is a single box and can only be scaled vertically, was reaching 60, maybe more than 60% of the biggest instance that we could have for that hosted service provider. So we were using the biggest instance we could, and we were reaching 60% CPU. We didn't know how much more traffic we were going to receive, so we had to do something, and we had to overcome this hard limit to scaling that the biggest instance we could have was imposing us. So one of the solutions we implemented, among others, was to divide this monolithic database into several databases, so we could scale the writers for each database independently. This was an investigation that needed to be done quickly because we didn't know how much more traffic we were going to receive. So for this investigation, the crucial tool was visual aids, as you can see here on this graph right here. These are the different tables we were writing to on the monolithic database, and this allowed us immediately to see that some tables were taking the lion's share of the writes. In particular, the visualization allowed us to detect the blue writes on this graphic, certain table that had a really unique writing pattern that was a very good candidate for making it an independent database. Why? Because the different pattern allowed us to treat each of the new databases, the spiky one and the more smooth one, with different criteria for optimization. So this is how it resulted. After that week, we switched over the weekend, and you can see that all the spiky behavior we had on the database was moved to a separate database that was optimized for a spiky behavior, while this one was, this change allowed us to optimize this one for a more smooth behavior, and we eventually took out some of those bigger bands, but we were off the hook, and we were able to have a single writer that wasn't being overwhelmed with writes. So as a conclusion, what helped us navigate through March? What are the lessons we learned from this very interesting experience and this test to our infrastructure? One of the most important things we leveraged was having easy and traceable changes in our infrastructure. So every change we did, every maximum we touched, every change in autoscaling was documented on our code, on our infra-as-code repository, and we could go back and know when we had changed a limit, when we had enabled autoscaling for something, etc. So keeping the infrastructure as code paradigm instead of maybe panicking and going full manual allowed us to have a trace of what we were doing, and going back then and discussing the decisions helped us extract various lessons that we used to keep going and keep improving. Our no heroes culture helped a lot in the sense of we didn't depend on anybody to adjust infrastructure. We could go, any engineer that was handling an incident could go and fix the infrastructure as they seem fit. So maybe change the maximum. Again, all these small changes, they were documented, and we have a empowered team with the no heroes culture that helped us going through this. So another point was the visualization of data, as we just saw. Having data from back to a year, maybe 2 years, being able to compare with last week, being able to identify the spikes, having visual data was tremendously helpful to have. So whenever you have a new service, go and create a good dashboard, prepare for wherever you think you may need in the future, and have that visualization, because that's where you are going to go when you need to take a quick decision, where you want to have a visual aid, you want to have a guidance or where to attack first. And for that, having data, analyzing it, maybe weekly, maybe seeing what the conclusions were from the Monday morning team, that's very important. So gather data, analyze it, and well, have a plan. Of course, we hadn't, actually executing, splitting database wasn't easy, of course, but we had thought for it. So even if you think, okay, what happens if we have 3 times traffic, we should divide the database. That's going to be a huge project, and you don't want to execute that project beforehand, but you want to have a plan thought out and say, well, if this ever happens, then we can go this way. If this ever happens, we should investigate this and go this way. A quick example for that was one of our external services in the middle of it started throttling us in the middle of the onset. So we weren't able to launch parts of the service, and we started having a degraded service because of the throttling. So this service had never failed us, never. This was the first time. And so since it had never failed us, we know it was a simple point of failure, but it was there, and we didn't seem logical to prevent that by implementing a secondary service, but we had planned for it. With it, if this ever fails, we can go this way. And we sort of prepared how to overcome that, and we executed that. We had a plan thought out, and we executed even if the pieces weren't there. So our busiest week, our busiest Monday, and our busiest hour are still ahead of us. Distance learning is here to stay. The game has changed, and we expect Back to School 2020 to be the biggest we have had and the biggest we will have, maybe. So we're honing up our resources for now. We're preparing the observability. We have a well-defined DSL for infrastructure as code and prepared to new challenges we're going to have. And we are prepared to adapt. So the lessons we extracted was always be prepared to react, observe, and pose. So thank you very much for listening to our story. Please, any questions you want, please ask them online, or feel free to reach me out after the talk for anything, any question, anything you feel was left out of the slides and you want more information about. So thank you very much.